Good morning. Today's lesson is going to focus on ester reactions. The first reaction we'll talk about is how esters are prepared. This actually is a lab that you will do in class at some point where we'll prepare esters and you'll get to smell the pleasant smells that they make when they're prepared. So this reaction you will actually see again and you will actually do in the lab. So what's happening here is we're taking carboxylic acids, we're reacting them with alcohols, and we're forming an ester in water. We call it a dehydration reaction. It can also be called a condensation reaction. So let me write that on the screen. In addition to it being dehydration, it can also be condensation. So all that means is that the reaction is giving off water, which you can see in the general reaction at the bottom of the page. You definitely need heat, so at the arrow, I would even include that little triangle to show heat. If I just put these two things together and I don't heat them in a little bit of lukewarm water or warmer water, the reaction isn't going to occur. The other thing that's important in this reaction is we need a catalyst, and it's catalyzed by a very strong acid. So you'd use something like sulfuric acid or hydrochloric acid or something like that. You'd add a couple drops to the vial for this reaction to occur. So what's actually happening here is, first off, let me just talk about this R1 and R2 so we're not confused there. We've seen this before, but the R1 and the R2 is just saying, okay, I have these two R groups, one on the alcohol and one on the carboxylic acid, and all that 1 and 2 is showing you is that it's showing you where it ends up on the product side. So you can see here I have R1 and R2 showing up on the product side, and it's basically just good organization, okay, just showing you where it moves so that you're not confused as the movement of those R groups on the carboxylic acid and the alcohol. So what's actually happening here, I'm going to switch colors, is we have the H on the carboxylic acid and the OH on the alcohol are going to be removed. And when they're removed, you can right away see that they are forming the water. HOH gives us H2O, which is water. And then I'm left with this R group that is going to then bond onto the carboxylic acid. So we have the R group then bonding onto this oxygen where the hydrogen left on the carboxylic acid. And so that's happening right here, and it's forming that OR group, which is part of the ester. The rest of the compound stays the same. The carboxylic acid portion all stays the same. The R1 stays in that same position, bonded to the C double bond O, and we have the R2 from the alcohol bonding onto the oxygen from the carboxylic acid, and then water formed. So that's just a quick breakdown of that reaction. We're going to look at some examples on the next couple slides to kind of give you a feel of showing that movement of the H and the OH forming the water and the R2 group bonding onto the leftover portion of the carboxylic acid. So here we have two reactions. These are actually shown in your textbook. I pulled these pictures right from the textbook. Not color-coded, so not my favorite thing with these reactions, but I can color-code them with my own colors. So let's take a look again at these reactions. We'll use a couple different colors here. We have ethanol, so this would be the portion that's going to bond onto this oxygen. And then this OH and this H are going to bond and form the water. So you can see over here this ethyl portion was the original ethanol, the alcohol portion, and you can see that the carboxylic acid here, that portion stayed the same. Nothing changed. The only thing that happened was that ethyl group from the ethanol bonded onto the oxygen to form ethyl butanoate. Again, you don't need to worry about the common names that are there in parentheses. You only need to worry about the IUPAC names. I also want to point out that we have the heat and the acid. Notice the double arrow there. I forgot to mention it on the last slide. That double arrow just means that this reaction is reversible, and we are going to look at the reverse reaction in this lesson today. Below, you can also see another reaction between ethanoic acid. Ethanoic is also called acetic acid. Acetic acid's vinegar. So you kind of should know acetic and ethanoic. You don't need to memorize it, but be aware of it, because you'll see acetic acid written more than you will see ethanoic acid. So that one, I would say, is one that you should just kind of keep in the back of your mind. We're reacting this with 1-propanol. Now, make sure when you are writing these reactions, and if you have to name the reactants, that you are writing that number 1 if it's attached at carbon 1 of the alcohol. Okay, so that's really important in these reactions. Again, what we have going on here is we have this H, let me switch back to my red here. We have H and OH coming off, forming our water. And then we have the propyl group bonding onto that oxygen, and you can see our product over here, propyl ethanoate. So it's taking the name from the 2 molecules that were used to form it. So 1-propanol becomes propyl, and ethanoic acid becomes ethanoate. So we end up with propyl ethanoate, and don't forget we also have that water. We also have those catalysts, or catalyst, the acid, and we need a little bit of heat there as well. So here we're going to actually write out the whole entire reaction. So our question is to show the reaction between propanoic acid and 1-butanol. We know that propanoic acid is 3 carbons, so we have 3 carbons there, and we know that 1-butanol is 4 carbons, and we have the alcohol group on carbon 1. So I've written out the compound structures, and now we're going to do this reaction. So in this reaction, I'm going to have that double arrow, which you can write a few different ways. You can write it as 2 arrows, one going forward, one going backwards. You can write it as the half arrows like I have it here. But either way, it doesn't really matter. Just show a double arrow there. We have acid. We have heat. Now, this reaction is going to remove an OH from the alcohol, an H from the carboxylic acid, and form the water. So we have one product, which is water. And I'm going to write the other product below. I have the 3-carbon carboxylic acid and the double bond O there, and that O has stayed on there. And now I'm going to take the 4-carbon chain that I had with the butanol, and I'm going to write it like so to form this ester. And I'll put all my little bonds to hydrogen there. And if we were to name this structure, we have 4-carbon alcohol, so that would be butyl. And we have a 3-carbon propanoic acid that now becomes propanoate. And we have butyl propanoate as our product. Now the next reaction I want to talk about is the reverse reaction of the preparation of an ester. Now we're going to do hydrolysis of ester. So now we're just going in the reverse. I'm going to start with an ester. I'm going to react it with water, and we call that a hydration reaction because we're putting water back into the system. It can be acid or base catalyzed. We're only going to talk about it in terms of being acid catalyzed. When we do the preparation of soap lab, that's a base catalyzed ester reaction. So we are going to look at base catalyzed at some point when we get to that lab. So for today, we're just going to focus on the ester acid catalyzed reaction. The reaction's kind of slow, and it does require heat. And the reason it needs the acid is because the reaction is slow. So the acid speeds it up a bit. And so let's just get right into it and take a look at these reactions. Okay, so here's the general reaction. You can see with the green background, and then an actual reaction right below that. So what you can see here is that we're taking the ester, again, showing the R1, R2 so that you can see where the R groups end up in the product side. We're reacting with water. We have some acid and some heat at the reversible arrows there, or the back and forth arrows. And then we're forming a carboxylic acid and an alcohol. So we're going in reverse of what we just did, breaking that ester apart into the carboxylic acid and alcohol. What's happening here is, and I like this because your book actually color-coded this one, the alcohol portion is going to come off. So that propyl group is going to come off, and it's going to bond with, remember, H2O can be written HOH, and so it's going to bond with that OH and form the 1-propanol, okay? Now, if this were not bonded on the first carbon, say it were bonded on 2-propanol, then you would say that the product would be 2-propanol, not 1-propanol. So it's all in where that oxygen is bonded onto the alcohol group. So we could have bonding here on the second carbon as well. And I'll show you a quick example of that on the next slide. So we have the propanol, 1-propanol forming, and then the leftover H here, let me just switch colors, the leftover H here is going to bond onto the leftover oxygen of the carboxylic acid portion, and it's going to form propanoic acid, which you can see over here as a product. So we have propyl propanoate forming propanoic acid and 1-propanol. So the last thing that I want to show you is just writing out the equation so that you can kind of see how you would write out the reaction. It's showing the acid hydrolysis of isopropyl pentanoate. Isopropyl, which is 2-propanol. So here's where I'm going to show you what happens when I have a structure bonded onto an interior carbon versus an end carbon. Now the reason I have the reaction at the bottom is because that's where we used 1-propanol. Now here we're using 2-propanol, the isopropyl group. The alcohol portion has the oxygen bonded to the second carbon of a 3-carbon chain. So that's going to change the product from being 1-propanol to isopropyl alcohol or 2-propanol. So I want you to see that distinction, the difference there with that attachment. So what's going to happen here is now we're going to kind of have this breaking apart right here of the compound. And so one of my products is going to be, and I'll have to write small over here because I don't have enough room. I have 2-propanol as one of my products, that OH coming from the water, and then the leftover H from the water is now going to bond onto the ester, so, or the carboxylic acid. So I have 5 carbons. Whoops. Carboxylic acids are always on the end. So that H bonded on there, and then I'll put all my hydrogens in, and I have pentanoic acid as the other product. So I have 2-propanol and pentanoic acid as my products. Again, on the arrow, I forgot to write this in. I have my H plus, and I have my heat because this is acid catalyzed. Now, I could base catalyze and use something like sodium hydroxide or calcium hydroxide or a strong base like that. We're not going to go through that reaction, but basically at the arrow you would have an OH minus to show base catalyzed. You would still need heat, and then on the product side, and you would have pretty much the same products going on there. It's just that you used a base to catalyze instead of the acid. And of course, here is some homework for you guys to try. It's on page 507 and 508 in your textbook. The numbers are listed there. It's also on the task sheet. And this is due in the Dropbox. So make sure you get that in the Dropbox. I am planning to post some homework keys, so it needs to be in the Dropbox before those homework keys are posted so that I know you did this on your own. I hope you're enjoying the snow and you are getting out there and helping your mom shovel or your dad shovel, or maybe making a snowman or something fun. But enjoy this time at home, and I hope you learned something about Ester Reactions. Have a great day, guys.